In this week's videos, we'll be looking at graphing exponential functions. In this first video, we'll be looking at what the graphs of exponential functions generally look like. We'll start off with the function y equals 2 to the power of x, and we'll draw a table of values. So we'll draw values for x equals minus 5 to x equals 6. We'll start here at x equals 0, 2 to the power of 0. Anything to the power of 0 is 1, so that has to be 1. If we take a value of x equals 1, 2 to the power of 1, anything to the power of 1 is itself, so 2 to the power of 1 is 2. Now 2 squared is 4. 2 cubed is 8. 2 to the power of 4 is 16. 2 to the power of 5 is 32. And 2 to the power of 6 is 64. So what we can see here is that these values down here tend to be very small. So 2 to the power of 0, 1, 2, 3, these numbers are all less than 10. But very rapidly you start to get up to numbers like 64. If we went to 2 to the power of 10, we'd have 1,000. 2 to the power of 20 would be about 1,000,000. And 2 to the power of 30 is around 1,000,000,000. These numbers become big very rapidly. On the left hand side, when x becomes negative, we can use the power law. A to the power of minus m equals 1 divided by a to the power of m. So 2 to the power of minus 1 is the same thing as 1 divided by 2 to the power of 1. So it's the same thing as 1 divided by 2 here. 2 to the power of minus 2, that's the same thing as 1 divided by 2 to the power of 2. 1 divided by 2 squared, it's the same thing here as 1 divided by 4. And the pattern here, and mathematics is all about patterns, is that we have 1 divided by 8, 1 divided by 16, and 1 divided by 32. Now these numbers, they're not becoming very large, they're becoming very small, they're rapidly approaching 0, but they'll never reach 0 because we'll always have 1 divided by some number. So let's look at what that looks like in a graph. Using GeoGebra, I'm going to plot y equals 2 to the power of x. So what we see here is on the left hand side, the function is very close to 0. And if we zoom out, that's very close to 0 there. If we were to zoom in, it'll take a long time, but eventually we'd see that function down here at minus 30 is close to 0. It'll take a very long time to scroll into that. So the function then starts sweeping up as we get to larger values of x. It passes through x equals 0 at a value of y equals 1, that's what we expect, and then it starts to become much larger, and it rapidly starts shooting up. So you can see here that even by the time it's up here, it's not even at 10. Imagine how big it's going to be when we get to 300. That number's going to be enormous. If we compare this to a parabolic function, so y equals x squared, you can see that it shoots up just like a parabolic function. In fact, it shoots up slightly faster. So if we're going to sketch a graph of 2 to the power of x, so to sketch a graph of 2 to the power of x, we start off with an asymptote on the x-axis, and the graph slowly becomes bigger. It passes through the y-axis at a value of 1, and then sweeps up very rapidly. So I'll just label that asymptote in. The other exponential function that we should look at while we're here is y equals 2 to the power of minus x. So where the graph of 2 to the power of x becomes very, very small for negative x values, the graph of 2 to the power of minus x becomes very, very large for those values. And the opposite is true on the other side, where 2 to the power of positive x is very, very large for positive x values. The graph of 2 to the power of minus x becomes very, very small on that right hand side of the graph. So if we sketch a graph of y equals 2 to the power of minus x, we start off on the left hand side here for negative x values at a very large value. The slope of the graph decreases, and then we have an asymptote here as well. So this graph on the left hand side is 2 to the power of x, and the graph on the right hand side is 2 to the power of minus x.